Hello everyone, I'm Ali. I'm a PhD student and a member of Dr. Diels research group. Uh, and I will be your tour guide through this virtual tour today. So basically in this lab we have high power lasers and we have three laser systems which I'm going to briefly introduce. Let's start with the UV laser, which is not a commercial laser. It has been built here. So it starts with an oscillator. You can see an oscillator here which has a neodymium yak crystal in it. It's gonna provide us with 1064 nanometer, 10 nanosecond, 110 millijoule laser pulses. Then these are gonna be amplified to 1, 2, 3, 4, 5, and 6. Those two white boxes that you can see. So it's a 6-stage linear amplifier, and it's gonna generate 1064 nanometer 3.5 joule 10 nanosecond laser pulses. Then these laser pulses are gonna go through a LBO crystal, which you can see here, and then they're gonna, through second harmonic generation, they're gonna turn into 532 nanometer laser pulses with 10 nanosecond pulse width and energy of 2.4 joule per pulse. Then these green laser pulses are gonna go through a water cell here, which you cannot see, it's in this box, and through SBS, or stimulated Brillouin scattering, which is a nonlinear phenomena, they're gonna turn into 200 picosecond laser pulses. And finally these green laser pulses are gonna go through another nonlinear crystal, a KDP, and finally the output of this laser is gonna be 266 nanometer, 200 picosecond, and 300 millijoule, and the rep rate of this laser is 1.25 hertz. So the second laser system, which is currently under development, is another laser system which is based on neodymium yak active mediums. Here you can see the oscillator and then one amplifier, and then there is going to be another 4 chains of linear amplifiers. This laser is using a different mechanism. It is a negative feedback and cavity dumped laser, so it's gonna generate hopefully something around 10 or 20 picosecond pulses at 1064 nanometer, and the rep rate of this laser is gonna be 10 hertz. Then these pulses are gonna go through a nonlinear process named cascade nonlinearities, and through this nonlinear process they're gonna change into 355 nanometer laser pulses. So basically this is also another UV laser system, which, as I mentioned, is currently under development. So the third laser system in our lab is a commercial laser system which is named Hydra. It is from Coherent. It's gonna generate 800 nanometer laser pulses, and it could work in 2 different modes. One is 10 hertz repetition rate, and the other one is gonna be 1 kilohertz repetition rate, and it's gonna generate around 10 femtosecond laser pulses with pulse energies up to 50 millijoule. We are currently trying to change this laser system to a 50 kilohertz laser system. At the back you can see a Lee laser, which is going to be the new pump for this laser system. And as a matter of fact, we also needed to design a new chamber for the main TISAF crystal in this laser system, as the current crystal holder is not capable of handling the 80 watt power that is gonna be the pump power at 50 kilohertz. So that's what we are currently basically rebuilding the region amplifier of this laser system. You can see here the current crystal holder. So this is going to be replaced with a new crystal holder, and it's going to be pumped with another laser so that we could achieve 50 kilohertz. So before I have mentioned the 3 laser systems that we have in our lab. We use these laser systems for studying of different phenomena, including laser filamentation, laser-induced breakdown spectroscopy, or laser-induced discharges. To study the laser filaments, we have a very phenomenal tool which is named aerodynamic window. You can see the aerodynamic window here, and this is the open section. Aerodynamic window is basically a barrier between a vacuum in the atmosphere, which is made of air. That gives us a unique capability to control the initiation or the starting of the filaments. So as I mentioned, we also do laser-induced breakdown spectroscopy or laser-induced discharge. For laser-induced discharge, we are doing it at the roof of CHTM, which I'm gonna also give you a short video tour of that laboratory. But the laser basically is gonna go to the roof through this window that you can see here at the ceiling of the lab. So later I'm gonna show you our lab also on the roof. But before going forward, I also want to show you a VMI setup or a velocity map setup, a velocity map imaging setup that we have built and designed and built here in our lab. This is another system that we are going to use to investigate the plasma generated by the laser filaments from different wavelengths. So hello everyone, we are now on the roof of CHTM. As I mentioned before, we have done and we are doing some experiments on our lab on the roof. As I showed you, there is a window on the ceiling of the lab that goes through the roof. This is the other end. So the lasers are coming through these channel up to here. Then they are going to be reflected by this mirror, and then by another mirror, and going through another lens inside that box, and then they're gonna go through this small hole in the wall of our lab at the roof. This lab is basically a huge double layered Faraday cage. Let's go see what's inside. So as I mentioned before, we are doing laser induced discharge experiments on the roof. So as you can see, the laser is going to come in through that hole, and it's going to go through these 2 spheres. As you can see, these spheres have holes in it, and we are going to study laser-induced discharge between these 2 electrodes, and we have done it for different distances between the electrodes. And these 2 are the power supplies for these experiments. We have also done some laser-induced breakdown spectroscopy experiments on the roof. As you can see, this is an aluminum sample here. The reason for that was that we wanted to see the effect of long-distance propagation of the laser on laser-induced breakdown spectroscopy experiments. Here also you can see the remaining